introduction. It's really nice and it's a pleasure to be at this symposium, and thanks for the invitation to actually giving a presentation. In that context, I will talk today about the methods or the systems we use for mining accessible chemical spaces, so spaces we can actually reach using AI-driven methods. So we all know, and in other presentations already, that finding the right molecule is extremely hard. It's really hard to find the correct right solution to your problem. And there are a lot of different estimations about the sizes of chemical spaces. One prominent number, which appears pretty often, is a magical number of 10 to the power of 60 for the estimation of the whole theoretical chemical space. Usually, some of them are already existing, so the known existing compounds are around 10 to the power of 8 molecules in here, and a typical company database like Sanofi or other pharma companies just contains a few million molecules. So if you start a new project and you want to explore the chemical space, these chemical spaces can be anywhere. They can be part of the existing compounds. They can be part of large virtual chemical spaces, which are growing in size, I imagine, nearly every day at the moment. But they can also be completely different, in a completely different space where we don't know anything yet. And just as a little comparison of the sizes we are talking about, so we can compare this to stars in the universe, but some people also estimated the number or calculated some rough numbers of how many grains of sand actually exist in the Sahara Desert. And they approximately said that's 10 to the power of 22, 24. So that's already comparable to very large chemical spaces. Still, the whole chemical space is extremely large and larger than these parts. So in a rough estimation, it would be easier to find one grain of sand in the Sahara Desert than finding the right molecule by chance. Luckily, we don't have to find this molecule by chance, but we can use a map or clever algorithms and navigations to actually come to the right solution quicker. So in that sense, we would not just sample the whole space we see here, but we would follow a direction or a path using data to come to the right conclusion. One method or one system which is used in drug discovery to actually navigate through the vast chemical space is the so-called, and already mentioned by Francesca before, the design, make, test, analyze cycle. So this is a key principle in drug design, that you first design some molecules, you make these molecules, so that you actually synthesize them. Obviously, you have to test them and analyze the data to make a new conclusion and do a next round of the DMTA cycle. So all in all, that's an iterative cycle. And in that cycle, we are doing a multi-parameter optimization to optimize sets of compounds we might already know and already test to find compounds with an optimal property profile. There are a lot of different ways where we can use machine learning or AI in this context. One, of course, would be AI-based de novo design, which we already heard a little bit about. And it can also be virtual screening and a large virtual chemical space exploration, or, for example, machine learning for property predictions. All in all, we are using AI and machine learnings to hopefully accelerate this DMTA cycle and turn the data we have into knowledge to find the optimal desired property profile and exploit in silico approaches for the design of novel compounds. When we want to use AI and machine learning for design of new compounds, we can, on the one hand, of course, predict properties using machine learning models, but we can also search for new compounds. So we do not only want to characterize the compounds we already have, but we want to find new compounds. We either search ultra-large or large virtual chemical spaces, which usually consist of readily accessible compounds, and we can select compounds from there with affinity predictions, similarity search, or ATME scorings. And if you want to go beyond that space, we can use de novo design to actually optimize and invent completely new compounds. At Sanofi, together with Biosolve IT in that context, we established our own Sanofi virtual space, which we can now routinely search. This is done by many different pharma companies or any kind of chemical companies already. One key aspect we focused on was firstly a selection of really robust reactions, or reactions which we are really sure that our library group can do them. So these are usually single-step reactions and some more complex ring closing reaction, but also a restriction of the building blocks to just the available and accessible building blocks we have, with 1 to 3 functional groups, which of course, if you have more than one functional groups, need to be protected. All of these building blocks are then grouped by their functional groups and subsequently filtered by to exclude incompatible substituents. So all in all, we are doing a quite careful and lengthy pre-processing of the building blocks to be as sure as possible that the building blocks and the content in the library are actually usable in the ongoing or in the subsequent reactions. In addition to that, to assess the speed, how we can get reactions, we proposed a layering of the virtual space, of our virtual space, where we first just look at 1 to 2 step reactions with reagents which are directly on stock in our library group, which is around 10 to the 9 molecules, and can extend this to 1 to 3 step reactions using all our in-house reagents, which in the end, in the summary, results to around 10 to the 14 molecules. And just as some numbers here, so our in-house building blocks, which are readily available for us, are around 200 building blocks, where we use around 28 common reaction, together with something like 10,000 bifunctional scaffolds and 100 trifunctional scaffolds. If you want to extend this and allow some more reagents, we combined it now with commercially available reagents from preferred vendors, which in the end allows us to access a space of around 10 to the 16. To make these spaces, or these chemical spaces, available and searchable, we first integrated it into a very simple search tool available to our medicinal chemists as well, and into Infinicy, which allows to search the complete chemical space, in addition to integrated external libraries like the enamine real space. To be as flexible as possible and be adaptable to the needs we have, we integrated a lot of different search technologies for the virtual libraries. If you want to just search for analogs or close analogs around a query compound, we are using simple 2D fingerprint descriptions and a Morgan ECFV4 type of fingerprint. As we cannot search the whole 10 to the 14 molecules with the fingerprint, we are enumerating smaller subsets with around 160 million molecules or random molecules from the internal spaces, which allows then to search them within a few seconds of time. If we want to do more scaffold hopping, so we do not want to directly assess an analog of the compound, we are also using 3D similarity search. In that context, we are using FastRox from OpenEye, which is an extremely fast shape similarity searching method. And as it is running on the GPU and has a preloaded library, it can search similar sized databases with 160 million molecules in just something like 1 or 2 minutes. So it's actually really fast to do 3D based similarity searching. And in the middle, we are also using the feature tree implementation from Biosolve IT with the Sanofi, with a chemical space generation. As feature tree itself is based on reaction definition and building blocks, so it can iteratively search through all the compounds based on the information about the building blocks. This actually allows to search extremely large spaces completely. So we can completely search everything what is inside of our Sanofi space, of course, with the limitation of having a certain descriptor of the molecules. So all in all, you can actually search extremely large spaces nowadays at a quite decent speed. And of course, these virtual chemical spaces have a lot of advantages. One advantage is definitely is that you have a defined and usually well-known chemistry with readily available reagents. And this, of course, allows you to have a quick access to the molecules. So if you have a starting molecule, a query molecule, and you do some searches, you can quickly explore around that hit, for example, an HTS hit from an experimental high throughput screen, or you can quickly follow up around a lead structure or rescaffold diverse molecules. Of course, virtual chemical spaces have a very clear disadvantage, and this is the limited chemical space which is available inside of the chemical libraries. Although the spaces are really large nowadays, it's still a limited chemical space. In that sense, we want to also extend beyond these limitations using generative AI algorithms in something like an in silico DMTA cycle. In that context, design and make would be a molecule generation, and the test and analyze would be an evaluation and a ranking of the molecules. The molecule evaluation and implementation here allows us to have a continuous and automatic improvement and update of all in silico models coupled to this evaluator, and which is also very important to have a panel of different scoring functions to be able to adapt your generation or your design to the particular project. As we want to have a process which is as easy as possible, we implemented it in an automated compound generation toolbox for the whole process, which then allows us to search in some way the complete chemical space with certain limitations using different generative design algorithms and integrate them directly into the drug design projects. As usually, each kind of molecule generation is covering a different type of the chemical space. We are combining different and a large panel of different molecule generators or AI algorithms. Some of them are rule-based generators, which means we are modifying the chemical structure based on predefined rules. Typical examples here is a match molecular pair analysis and use the transformation derived from those, or some typical metchem transformation and fragment-based approaches. We are also extending or using typical generative AI algorithms, which, for example, allows us or makes it possible to search latent space representations of the molecules within variational autoencoder. In our context, we're using junction tree variational autoencoders, or typical language-based models, which we have seen in the previous presentation as well, using recurrent neural networks to generate smile strings and optimize them towards your property. If we want to generate molecules and optimize them towards a property, we of course also need to know which property we want to optimize. And as this is very different from project to project and from question to question, we are implementing a large panel of scoring functions, a toolbox of scoring functions, which can be combined in any way you actually want to have it. So this is ranging from 2D and 3D ligand-based scoring, which allows an analoging mode or more scaffold hopping mode, to structure-based scoring functions where we directly employ 3D docking information in this generation. Although this is of course much more time consuming, it allows to do scaffold hopping and optimization in a pocket directly. And of course, also using all kinds of machine learning models for target bioactivity models, or the typical panels of APME properties like permeability or metabolic stability with Fuscam properties. A typical AI generation workflow is then your training or you implement the known chemistry into your molecule generators. This can be, as mentioned, recurrent neural networks, fragments, but also just virtual libraries and other tools. And usually you're generating a couple of molecules. The molecules are evaluated and ranked using the defined scoring functions for the specific question. And using that, you are updating the behavior of your system and change the behavior to drive the generation in the region where you actually want to be. In the sense of the deep neural network methods, you usually use approaches like reinforcement learning for virtual libraries or autoencoders. You can also use a simple global optimization to actually drive the optimization into the region where you want to be. In the following, I want to focus on one particular reinforcement learning method, which is very interesting in our design methods, which is a fragment-based reinforcement learning method, which is called DeepFMPO. This method was developed by a former colleague of mine at AstraZeneca, Jonas Boström, and we integrated or used this method in our drug design project, and it actually turned out to be very efficient and delivering very nice results. The key idea here is that you have a rule-based fragmentation of the structures, where you have some starting structures, which are called lead structures, and a pool of fragment molecules or molecules which serve as fragments. And these fragments are then rearranged or arranged in a tree where similar molecules or similar fragments are close to each other. So if you would change a fragment close to each other, they should also be chemically rather similar. In the last step, you're then building a reinforcement learning-based actor-critic model to actually learn which modification in the compounds are beneficial. As this original implementation turned out to be very interesting, and it allows a focused exploration of the chemical space close to the lead structures and the provided fragments. We implemented this in our scoring scheme and added several extensions and additions to the approach, like additional splitting and fragmentation rules, which in the end, where we in the end wanted to teach even more chemistry to the generator. So we just submitted a publication around this, and some key steps here is how the splitting of the molecule is actually performed. So in the most easiest way, and in the way which was in the original implementation already, is to split the molecules by a predefined smarts rule. So if you have a molecule like on the top, you're actually searching for bonds which can be broken, you fragmentize them, and then you have fragments with different numbers of attachment points. And in the generation of new molecules, you obviously change fragments having the same number of attachment points to allow a rearrangement or a recreation of a molecule. In our extension, we added the possibility to actually directly use a reaction definition from RxN files. So this actually allows that you can draw a retrosynthetic route for the chemistry you have in your library or in your chemistry group, and then directly use this information in the generation or the splitting of the molecules. So this gives us then molecules or fragments which are actually following a retrosynthetic route or idea. In the next edition, we also wanted the fragments to be as close to the available chemistry. So instead of simply fragmentizing a pool of molecules, we directly use all the building blocks we have in our virtual library. These virtual library or these building blocks in the virtual library are already pre-processed, that they can be used in the enumeration or creation of new molecules. And this format is actually directly compatible or directly usable in the fragment framework of this generation work. So we can directly use the fragments from the virtual library to apply or the reinforcement learning process and generate new molecules. Nevertheless, now we either are using reactions or building blocks, and in a way we can still diverge from chemically accessible molecules. So in the end, we also combine these two routes to actually have something like a deep virtual library where you have reaction information and building block information, and you couple those together, like in the illustration on the top. You have, if you want to build a tripeptide, you can obviously start from amino acid with two functional groups and couple it to acids and amines on the other hand. So this in total gives you something like 400 billion possible molecules. And instead of searching all of these 400 billion molecules or building a space which you search with a specific descriptor, you can now actually search the virtual library with a reinforcement learning approach. And the key advantage here is that we can, in principle, use any kind of descriptor or scoring function in the search of the new molecules. In the last step, we also wanted to evaluate these methods in something like a drug design setting. So as we already implemented or used the flexible scoring system, we can use 2D and 3D similarity. We now took 15 targets from the Campbell database and first separated all these targets into separate data sets, and then clustered all active molecules from one target, that you have a clustering of the molecules and active molecules for each specific target. Then for each target, we selected the most active molecule from one of the clusters. It should be a reasonable cluster, that it's something, a drug-like query molecule or a drug-like cluster, and also having a reasonable size. So it shouldn't be just a singleton one of these clusters. And then we are using that active molecule as a query molecule for the reinforcement learning. So either with 2D or 3D similarity. As a test, we also excluded 20 neighbors around this query molecule from the same cluster as an independent test set. So we then wanted to see how many of these 20 molecules can we regenerate in the reinforcement learning, and used up to 50 molecules from the remaining cluster as the starting points, so the lead structures. So they are chemically similar, of course, to the query and the neighbors, but they are not identical. And all other structures serve as the pool where we generate the molecules. And in a rough summary, we can actually see that in most cases, we get similar molecules from the test set, and also the query is recreated in several cases. So here you can see a summary of all the different targets with a normal smarts-based splitting and an RxN reaction file splitting with 2D and 3D similarity. And on the one hand, you can see a clear difference between 2D and 3D scoring, which is pretty obvious, of course, but it's nevertheless important information for us to see which scoring functions we want to use. And you can also see a clear difference between smarts and RxN splitting, which basically tells us that each of the method covers a different kind of chemical space, and the combination of different generators actually offers much larger flexibility. To be usable in a drug design project, we implemented all of these generations in an automated design workflow, which we simply call the digital team member. And in this approach, we say if we have novel project data for one of our projects, we are doing automated data extraction and use this data to update the machine learning models for this particular project, and then use the most recent and active inhibitors as seeds for AI designs. In this AI-based de novo generation, we use different generation methods and reward scoring functions, and also couple them with Metcalfe transformation and matched molecular pair. So we're actually doing quite a lot of generations for one iteration of the workflow, and then pool all of these data together and filter it for uniqueness and novelty, and also perform some post filtering for these hits. One key aspect of this workflow is that it's actually simplifying the idea generation process and helps a lot to keep in silico models up to date, and also allows to tailor and adopt the workflows for each project, which makes it much easier for the projects to take up ideas from these workflows. If we have our hits from the post-processing, usually we explore or discuss these within the project teams. Some of the hits are so interesting that they are directly proposed to synthesis. Others are interesting from one part of the molecule, or they might be difficult to make it in the whole molecule. So, but these can still generate new ideas. For example, taking that scaffold and add it to another part of the molecule. And obviously, especially in very early parts of our projects, we follow up the AI hits in virtual libraries, for example, our own Sanofi virtual library, or other commercial libraries to actually get a potentially very quick access or synthesis of the molecules in our in-house library group. And I want to conclude or end here with a rough example where we extended the SAR and of course through a combination of our virtual libraries and AI-based generation tools. So in the end, the combination of these two methods actually offers quite unique possibilities. So in that particular example, we had an early HTS hit, which already showed a decent activity in the enzymatic assay, but was completely inactive in the cellular assays and also had some quite high metabolic liabilities. So in the first step, we did some virtual screenings in the enamine real space and ordered around 80 diverse compounds. And they actually delivered a new core within this series, which still has similar liabilities as the original hit. But we were then able to rescreen additional enamine libraries and get around 100 new compounds around this hit, and actually obtain a lot of new SAR information around these two new series. In the end, we used our AI-driven optimization within the medicinal chemistry project teams, and also combined this with the information from other series to actually find a very active molecule, which was also cellularly active and had a much improved ADME property profile. So in conclusion, we see the AI-based de novo design as a very useful tool to successfully mine chemical space, and we actually see that we can find highly novel active molecules and stimulate the projects to new ideas for further synthesis. And in particular, the combination of several molecule generation tools and reward functions is very useful, as you have a broader search of the chemical space and adapt the scoring to the specific need of the project. Usually, as already mentioned before, synthetic accessibility is key to AI-generated molecules, and that's why we think the fragment-based generation approaches are particularly promising, especially in combination with chemistry rules. And together with the integration of virtual libraries, this actually allows a very quick synthetic access and an automatic way of suggesting new compounds. And with that, I want to thank a lot of collaborators and colleagues at Sanofi, and also our colleagues here at Biosolve IT for supporting us in building the spaces, and of course for giving me the opportunity to present the results here. And thank you. If you have any questions, please feel free.